Hi, this is Barrett Givens, and I want to talk about a way that we can think about interiors of sets that will help us when we're trying to find the interiors of different sets. So this is a theorem. Let A be a subset of a topological space X. Then Y is in the interior of A if and only if there is an open set U with Y, element of U, subset of A. Okay, that should look very familiar. There's an open set U with Y, an element of U, subset of A. That whole phrase there, that's actually the same as a definition that we've already learned. Another way of saying this is that A is a neighborhood of Y. So another way of saying it is that the interior points of A are all the points that A is a neighborhood of. The interior points of A are all points that A is a neighborhood for. Okay, so that's another way that we can think about it. So we're kind of tying all these concepts together. Let's go ahead and prove this theorem. This theorem is an if and only if, and so we have to go both directions. Okay, so let's go the forward direction. Suppose Y is in the interior of A. The definition of interior is that it's the union of all of the open sets inside of A. So Y is somewhere in that union. What does it mean to be in a union of sets? It means you're in at least one of them. So Y is an element of the union of all open sets, all open subsets of A. Which means Y is in, to be in the union means you're in at least one of them. Thus Y is an element of at least one open subset of A. Well, that's actually in words what I have there highlighted in blue. Y is in some open subset of A, okay? So there exists open U with Y in U subset of A. All right, that's the forward direction. It's almost just by definition. To be in the union means you're in one of them. And so whatever that one is, we'll call it U. And then we have the thing we want. All right, now what about the other direction? Suppose for some open U subset of A, Y is in U. Well, then U is one of the sets that gets included in this union, right? U is one of the sets that gets included in this union. So if I have a whole bunch of sets and I union them all up, well, each one of them individually is a subset of the union, right? And so U is a subset of the interior of A. Another way to say that is that the interior A is the largest open set containing U. So it's the largest open set contained in A. Interior of U, let me start over. Interior of A is the largest open set inside of A. U is some other open set inside of A. And so U has to be inside of the interior because this one's the biggest. Okay, the interior of A is the biggest. All right. And then recall, Y is in U. So these two things together, well, Y is in U and U is a subset of the interior. That tells me that Y is in the interior. Okay, so I did two directions on this proof. And so now we know that we can think of the interior of A as all the points that A is a neighborhood for. So that will help us when we're trying to figure out what the interior of A looks like. Just think of it as like, which are the points that A is the neighborhood of? Those are the interior points. All right. Thank you for listening.